I was making a glass of lemon water Nimbu Pani yesterday afternoon. It's really hot outside, typical summer heat, so I use cold water right from the fridge. I put the sugar in, and I'm stirring and stirring and stirring.
And it just won't dissolve.
It just would not dissolve. The grains were just sitting at the bottom of the glass, mocking me.
That is a classic summer tragedy. I bet if you had used warm water first to dissolve the sugar and then added the ice, it would have vanished in seconds.
Exactly, and that got me thinking about these weird contradictions we see in the kitchen. Sugar needs heat to dissolve properly, but then you think about a soda.
Hmm.
If you heat up a Coke or a Pepsi, it goes flat. The gas, the fizz, it just leaves. It's the exact opposite behavior.
It is a bit of a paradox, isn't it? Why does nature treat a solid like sugar so differently from a gas like carbon dioxide?
That is exactly what we are cracking today. We're looking at Unit 1, solutions, and specifically the concept of solubility. And for everyone listening, I know what you're thinking. You are thinking, solubility, that's easy. Things dissolve. Next topic, please.
Ah, but that is the trap. That is exactly where students lose marks in the board exams. Understanding solubility is the only way to predict if a chemical reaction will actually happen or if your product will, turn into a precipitate.
So it explains why some things just hide in solution and others become visible solids.
Exactly. It's the difference between a clear solution and a cloudy mess in your test tube. This is simpler than the textbook makes it sound.
So the mission today is simple. We are going to move beyond the textbook definitions. We're going to visualize this so clearly that you can write the answer in your exams with your eyes closed. Let's dive deep into solubility.
Let's do it.
Okay, so let's start at the very beginning. The zero-level explanation from our source material. I think a lot of us, when we start Class 12 chemistry, have this binary switch in our heads, like salt is soluble, sand is insoluble, yes or no, 1 or 0.
That is the first fundamental mistake. At the simplest level, solubility is not a switch. It's a spectrum. It is a quantitative property.
Quantitative, meaning it's all about the numbers.
Precisely. It's not just does it dissolve, it's how much. Think of it as a capacity limit. Solubility is specifically about the maximum amount of a substance that can dissolve in a specific amount of solvent, before the solvent simply refuses to take any more.
Refuses to take any more. That implies there's a struggle happening. I really like the visualization in the notes for this. It asks us to imagine a dance floor.
Yes, this is a beautiful image to keep in your mind. Imagine a crowded wedding reception. The music is playing. The dance floor is your beaker. The people already dancing, those are your water molecules, the solvent. They're moving, flowing, interacting with each other.
Okay, so the music is playing, the water molecules are dancing. Now we add the solute. Let's say salt.
Right. The salt ions are the outsiders trying to join the party. Now, at first, there's plenty of space on the floor. The water molecules, the dancers, are welcoming. They surround these outsiders, they hold hands with them, and they pull them into the dance. This is dissolving.
But the dance floor has a limit. It's not infinite.
Exactly. Eventually, every water molecule has a partner. The floor is packed. It is houseful.
And if another outsider tries to step onto the floor,
They can't. There's literally no one to dance with. So what do? They have to stand on the sidelines. In chemistry terms, they sit at the bottom of the beaker as a solid precipitate. That state where the dance floor is completely full is what we call saturation.
saturation. Okay, now this is where I want to push a bit deeper because the sources mention something that I think is very counterintuitive. When we see that pile of undissolved salt at the bottom of the beaker, it looks, well, dead. It looks static. Nothing is moving.
It looks that way to the naked eye, yes. But if you had microscopic vision, if you could see the atoms, you would see absolute chaos.
Chaos. But it's just a pile of salt.
We call it dynamic equilibrium. Even when the solution is saturated, the particles never stop moving. Some of those salt particles sitting at the bottom are actually jumping into the solution.
Wait, so they are dissolving, even after saturation?
They are, but here's the catch. At the exact same moment, an equal number of dissolved particles from the liquid are getting tired, crashing back into the solid pile and recrystallizing.
Oh, I see. It's like a revolving door at a mall or a hotel.
That is a perfect analogy. 10 people enter the hotel through the revolving door and 10 people leave. The total number of people inside the lobby stays the same, but the faces are constantly changing.
That is dynamic equilibrium.
And that's what's happening. The rate of dissolution equals the rate of crystallization.
That is a very important concept for the exams. Examiners love asking about equilibrium. It's not a static state, it's dynamic. So if we had to give our listeners a proper insert-safe definition to write down something that gets full marks, what's the anchor definition?
Let's be very precise here. You should write, solubility is the maximum mass or moles of a solute that can dissolve in a given mass or volume of solvent at a specific temperature and pressure, forming a saturated solution.
I noticed you emphasized at a specific temperature. That is the key phrase, isn't it?
It is the trigger line for misunderstandings. Students often think solubility is a fixed number, like a permanent ID card for a chemical, like solubility of NCl is X, full stop.
But it's not.
It is not. Solubility changes drastically if you change the temperature.
Okay, we're definitely going to get to that temperature magic and the weird behavior of gases in a moment. But first, I want to cement this idea of capacity with another analogy from source B2. I think every student in India can relate to this one. The parking lot.
Ah, the classical analogy. It works perfectly because we have all seen it.
Right. Imagine a parking lot outside a busy market. The parking lot is your solvent. The limited spaces, that's the capacity. The cars trying to park. That is your solute.
And saturation.
Saturation is when the security guard puts up the house full or no parking board. Every spot is taken. If a new car comes, it just has to wait outside on the road.
You precipitate.
It precipitates. It cannot enter the solution phase.
Correct. And this helps explain why we get precipitate. It is simply an overflow of cars. There is physically nowhere for them to go.
Now, here's where it gets interesting. What happens if we heat the solution?
Hmm.
In our parking lot analogy, heating is like, what? Suddenly doing some construction work.
Or simply painting narrower lines so more cars fit. Or maybe building a second floor to the parking lot.
Exactly. You add more lanes.
Right.
Suddenly the capacity increases. The cars that were waiting outside, the precipitate, can now park.
So for most solids, heating increases solubility. That's a very sound analogy.
And, this concept exists for a reason. It wasn't just invented to torture Class 12 students.
I hope not.
I often feel like some concepts are invented for torture. But why does this one exist?
Well, chemists needed a way to predict phase behavior. Imagine you are a chemist in the 17th or 18th century. You mix two clear liquids, and suddenly, bam, it turns cloudy. Why? Without the concept of solubility, it would just look like magic or alchemy.
So the tables of solubility data were created to predict that cloudiness.
Yes, they solved the problem of prediction. Without this data, we wouldn't know if mixing substance A and substance B would stay clear or turn into a mess. It creates a map for chemical reactions.
Okay, I want to take our listeners through a mental movie. This is from source B2B. I want everyone listening to close their eyes for a second, unless you are driving or walking to tuition, of course.
Safety first. But if you are at your desk, visualize this.
Picture a glass beaker of water sitting on a table. It's at room temperature, say 20 degrees C. Now, take a mental spoon of sugar and dump it in.
Watch the crystals falling through the water.
They swirl around, they disappear, they dissolve. You add another spoon, gone. You keep adding. Eventually, the sugar stops disappearing. A white pile forms at the bottom.
The solution is saturated.
Now zoom in. Really look at that pile of sugar at the bottom. It looks still, but remember the dancers.
The molecules on the surface of that crystal are vibrating. They are breaking away into the water, and others are sticking back on. It is a busy surface.
Now, in our mental movie, someone turns on a heater under the beaker. The water warms up to 50 degrees C. What happens to that pile of sugar?
The water molecules start moving faster. They have more kinetic energy. They are banging into the crystal surface harder and faster.
And the result?
The pile disappears. The water now has more room for the sugar because the water molecules are more energetic. They can keep more sugar molecules in suspension. The parking lot has expanded.
That visualization really helps. It shows that solubility isn't just a number in a book. It's a physical battle between water molecules and the crystal structure.
And this brings us to some concrete examples. Because in the exam, you won't just get asked for definitions. You might get asked about specific substances or trends.
Let's talk about our best friend, sodium chloride, common salt.
NaCl, the classic example.
So looking at the data, at room temperature, you can dissolve about 36 grams of salt in 100 millimolars of water. That's the limit, the 37th gram. It'll sit at the bottom.
Correct. Now, knowing what we just discussed about heat, if you heat that water to 80 degrees C, what do you expect?
Well, based on the parking lot theory, it should dissolve a lot more.
You would think so. But salt is actually a bit of an outlier. The solubility goes up, yes, but only to about 39 grams.
Wait, really? Only a 3-gram difference?
Yes. The solubility curve for salt is very flat. Compare that to something like potassium nitrate. If you heat that up, the solubility skyrockets. But for salt, the gain is marginal.
That is a great specific detail to remember for the exam. Salt is stubborn. But still, the principle holds. Heat usually helps solids dissolve. Now, what happens if we reverse the movie? You have saturated water at 80 degrees C with 39 grams of salt dissolved. You let it cool down to room temp.
The capacity shrinks, the parking lot closes the extra lanes, the water says, I can no longer hold these extra 3 grams, so the salt has nowhere to go. It reappears. It precipitates out of the solution.
This is actually used in technology and industry, isn't it? It's not just a lab trick.
Oh, absolutely. This is the basis of a technique called recrystallization. It's how we get pure chemicals.
How does that work? Walk us through the logic.
Imagine you have an impure chemical. Let's say you synthesize aspirin in a lab, but it's mixed with some dirt or unreacted starting material. You dissolve this dirty mixture in a solvent that is very hot.
So the solubility is high. Everything dissolves.
Most of it dissolves. You filter out the dirt that doesn't dissolve. Now you have a hot, clear liquid containing your aspirin. Then you let it cool down slowly.
And as the temperature drops,
Solubility drops. The aspirin can no longer stay dissolved. It creates beautiful, pure crystals that fall to the bottom.
but what about the impurities, the junk we want to get rid of?
This is the genius part. The impurities are usually present in small amounts, so even when the solution cools down, the parking lot is still big enough to hold that small amount of junk.
So the junk stays dissolved in the liquid.
And the pure stuff crystallizes out. Precisely. It is the primary way pharmaceutical companies purify drugs. It's a purification engine.
Now, we have been saying heat makes things dissolve better. Heat expands the parking lot. But there's a trap here, a massive gotcha moment that examiners love.
Yes, the counterintuitive example, the one that breaks the rule.
You might think heating always helps things dissolve.
But actually, that is only true for most solids. For gases, it is the complete opposite.
The gas logic, this is where my soda example comes back in.
Exactly. Think about it energetically. When a solid dissolves, it usually needs energy to break apart its crystal lattice. It likes the heat. But when a gas dissolves in liquid, the process is actually exothermic. It releases heat.
So nature opposes the heat.
In a way, yes. But think of it simply. Gas molecules are energetic. They want to fly around. They want to be free. If you heat the solution, you are giving those gas molecules even more kinetic energy.
They want to escape.
Exactly. Heating makes the gas move so fast it breaks the bonds with the water and escapes into the air. Heating decreases the solubility of gases.
This explains so much. This is why if you heat water in a pan before it even boils, you see those tiny bubbles forming on the side. That isn't steam, right?
No, that is not boiling. That is the dissolved air, oxygen, and nitrogen escaping because the water got too hot to hold them.
And it explains why warm soda tastes flat. The carbon dioxide, the fizz, has escaped because the liquid got too warm.
It also explains a very sad biological fact. In summer, if a lake gets too hot, fish can die. Not because of the heat itself, but because hot water cannot hold enough dissolved oxygen, the fish essentially suffocate.
Aquarium water bubbles when heated, soda goes flat, fish struggling in summer. It is all the same principle, and it's the exact opposite of the sugar example.
And this is where the examiners love to trick students. They will ask a question like, how does temperature affect solubility? And if you just answer, it increases it, you lose marks.
You have to split your answer.
Yes, you must specify. Increases for solids, decreases for gases. You have to show that distinction.
Okay, that is a golden rule right there. Let's make sure our listeners have these key points locked down. Source B4 calls these exam-safe clarity lines.
These are the takeaways you need to have at your fingertips.
Let's break them down. If you are taking notes, this is the time to write. Clarity check number 1.
Solubility is quantitative. It is a specific number, grams per 100 milliliter or moles per liter. It is not a feeling. Do not write vague answers like, it dissolves well. Be precise.
Clarity check number 2.
Saturation. A saturated solution contains the maximum dissolved solute at that temperature. Adding more does nothing. It will not dissolve. But remember, it is a state of dynamic equilibrium.
Point number 3. We just covered this, but let's say it again for the backbenchers. The temperature rule.
For solids, hotter usually equals more soluble. For gases, hotter equals less soluble. If you want to sound fancy, you can mention this relates to Henry's law for gases, which we will cover in another deep dive.
But one more point, something simpler that often appears in multiple choice questions, the common ion effect.
Ah, yes. Simply
Yeah.
put, if you have a saturated solution of salt, say sodium chloride, NaCl, and you add another substance that also contains chlorine ions, what happens?
Well, going back to the dance floor, if the floor is full of NaCl and you try to shove in more Cl,
It disrupts the balance. The parking lot is already full of chlorine cars.
so the solubility drops.
Yes. Adding a common ion decreases the solubility of the salt. It shifts the equilibrium back towards the solid precipitate.
This is important because in the exam, they will try to trick you. They won't just ask, what is solubility? They will say, what happens to the solubility of AgL if you add NaCl?
And the answer is, it decreases because of the common chloride ion.
So let's wrap this up with a short summary. We've covered a lot of ground in a short time.
Indeed. We started with the core idea. Solubility is the maximum capacity of a solvent. It's like a parking lot or a dance floor.
We visualized the beaker. At room temperature, the sugar sits at the bottom. Heat it up, and the sugar dissolves. The parking lot expands for solids.
But we must remember the key distinction. Hot water holds more sugar, but it holds less gas.
And finally, saturation is not a dead end. It is a dynamic equilibrium. Particles are coming and going, entering and leaving the dance floor constantly, even if the pile looks still.
If you can hold that mental movie in your head, the vibrating crystal, the parking lot, the escaping gas bubbles, you will be able to answer any conceptual question on solubility.
Absolutely. You have got this, Class 12 champions. Solubility is just the beginning of Unit 1, but it's the foundation. If you get this right, the rest of the chapter, it all flows smoothly.
Keep visualizing the molecules. Chemistry is much easier when you can see it in your mind.
And here's a thought to leave you with. We talked about how gases leave when you heat a liquid. Think about scuba divers. When they dive deep, the pressure is high. More gas dissolves in their blood. When they come up too fast, the pressure drops. The gas comes out of solution.
That is the bends.
Exactly. Bubbles in the blood. It's a solubility problem. Think about that next time you open a soda bottle. That is all for this deep dive. Go crack those problems.
All the best.